Hello and good evening to all who are present here. My name is Paris Palkar, and I would like to welcome you all for the session number 3 on learning CFD using OpenFOAM. In the previous two sessions, we have understood how to install OpenFOAM, how to set up the run directory, how to copy a case, and basic meshing using block mesh. Today, we are going a bit intermediate level and we are going to learn SnappyHexMesh. Yes, I would like to welcome you all who are present. And this is going to be a very detailed session using SnappyHexMesh. My name is Paris Palkar, and I'm working as a research assistant at the FOSSEE CFD team in IIT Bombay. And this is the session number 3 for this course. So, before proceeding, I would just like to introduce to our team Prabhu sir, Chandan sir, and Payal ma'am. Prabhu sir is leading the FOSSEE project, and he is also working as the professor at Department of Aerospace Engineering at IIT Bombay. Chandan sir is leading the CFD FOSSEE project. He is working at the University of Birmingham in the Department of Aerospace as a professor, and Chandan sir is also visiting professor at IIT Bombay. And Payal ma'am is working as a senior project manager under the CFD project. So yeah, in the previous session we learned about some basic meshing, but now we are going a bit intermediate and advanced level meshing concepts. And now we will understand what is meshing. So see, this is a bicycle on which a rider is riding his bicycle, but the way he is sitting will depend the aerodynamic drag he's going to experience. And in races, it is extremely important to sit in an optimal position to get the best optimum efficiency. So meshing is nothing but dividing a continuous geometry into a collection of smaller and simple parts. So if you can see, if we take this bicycle rider and zoom in, we have discretized him into some smaller domains. And in these smaller domains, our CFD equations will be resolved. Okay. So, what is SnappyHexMesh first? So, SnappyHexMesh, we generally call it as SHM, is an open form utility, same as BlockMesh, and it is used to generate some high quality meshes for complicated geometries. BlockMesh can be utilized for simple geometries, but for some complicated geometries, we generally use SnappyHexMesh, or either we do simulations in ANSYS. We do the meshing part and we import them back to OpenFOAM. So this utility, what it does is it generates 3D meshes. As I have told that OpenFOAM is built upon finite volume methods, C++ methodology. So basically OpenFOAM will generate 3D meshes first, and then we have to take that 3D block and convert it into a 2D mesh size if we want to work on 2D problems. And it is an iterative process where if we are interested to add refinement, we can do using the interested regions. And same as mentioned in the previous session, the mesh will be again stored in the constants polymesh folder. I have explained this in the block mesh session. If you are not aware of the mesh information storing, you can refer back to the previous sessions. I have explained it there. So, what is the workflow in SnappyHexMesh? So, what we generally do is to simulate some complicated geometries. We need two parts. First is the background mesh, and second is the geometry file or the STL file that we are using. So, this background mesh can be generated using our block mesh, or we can use any external mesher as well for this. And we will create a background mesh. And for our geometry STL, we can use the CAD modeling software like CATIA or FreeCAD or SolidWorks. Anything is possible. We can also use Blender to export the STL into the OpenFOAM environment, and we can mesh it using background mesh and geometry. And once these two processes are done, then we club them into SnappyHexMesh, and SnappyHexMesh converts it into an OpenFOAM readable mesh. We will learn about it in detail. So let me just go through my slides. And yes, the process starts with the creation of background meshes. The background mesh, as I told, it is created using block mesh, and block mesh generally makes a pure hexahedral meshes, and that is divided in your overall domain. And along with that, any, let us say, if you want to do an external aerodynamic simulation, so for that we are going, let us say if you import an airfoil, so that airfoil will be generated in your CAD modeling software. You can just import the coordinates, make the STL. STL is nothing but the stereolithography format, and any complex structure is also suitable, and that can be imported. And then both the background mesh and the STL geometry are processed through SnappyHexMesh dictionary. So in one part we are making the background mesh using block mesh, and second part we are making our geometry using any CAD modeling software. So to generate any complicated mesh, there are three criterias. The first, the mesh must consist of pure blocks purely of hexes. This is hexahedral blocks, and the cell aspect ratio should be approximately to 1. Uh, s- Aspect ratio is nothing but the ratio of the smallest length to the highest length, and if the ratio is 1, then the two quantities are equal. That means both smallest quantity and highest quantity are having the same length, hence the aspect ratio is 1. Generally we achieve highest aspect ratio or aspect ratio near 1 using block mesh only, and there must be only a single cell edge intersection. We'll get to learn about it in the later part. So yeah, as we saw in block mesh, the block mesh file consists of some parts, that is scale, vertices, blocks, edges, and boundaries. So this is explained in the block mesh section. You can refer back again. And now we are going to understand the same part for SnappyHexMesh. So, as we saw, there are 4 to 5 blocks in block mesh. Same, there are 3 blocks in SnappyHexMesh. Okay, so this is the castellated mesh control. This is the first block. This is snap controls. This is the second block, and this is the third block, that is add layers. And also, there is a section called mesh quality control. We can define it after we have created our mesh, or we can define it as a separate file as well. Okay, I'll show you the file as well, so please do not worry. Here I have given some commands. I will explain them later. Okay, so yeah, you might be wondering what is an background mesh. So here, this was a simulation that I carried out for room ventilation. So from this room is hot, the room here is hot, and we are injecting some cold air from this section, and it should travel, go in this pipe and cool the room. Okay, so for that we will need, and I have simulated it in open form. So for that we are going to need a background mesh. So what I did was I generated a background mesh using block mesh. So here I have just pasted my STL and experienced how my STL will look like. And once I have run the SnappyHexMesh utility, then the block mesh and my STL was merged into a mesh, and I was able to generate a successful mesh using Snappy. Yes, so let us understand everything in small sections. First part, what is the background mesh? The background mesh is nothing but the mesh that is generated using block mesh. And again, as we discussed, the aspect ratio should be near to 1. And it is a basic level mesh, and it covers almost entire of your domain. And let us if we are importing an airfoil, so we generally keep the domain bigger, so that our airfoil gradually is adjusted in this big domain. Okay, so first part of background mesh is done. Now these are the commands that is executed in SnappyHexMesh. So in second part, that is refining the background mesh, what generally happens is, if we have imported our STL in the background mesh, cell splitting starts in the area of interest, and this is done in the castellated mesh control. So if you see, the first part is castellated mesh controls. So if you have your background mesh, and now you're importing an airfoil here. So the cell splitting will start, and cell will be splitting according to the edge surfaces. There is a command how to find out. I will explain this. And geometry edges are defined in the surface features dict or surface features extract dict. In OpenFOAM 9, this is the difference in two OpenFOAMs. In OpenFOAM 9 or the foundation version, the surface features file is known as surface features dict, and in OpenFOAM ESI versions or 2412 or 2506, it is written as surface feature extract dict. So this is the basic difference in both the syntax. And generally how refinement works, so let us say if you give a refinement level of 1, so if this was your base cell, it will be splitted horizontally and vertically into two levels if you give level 1 of refinement. If you have given a level 2 of refinement, so this block again will be splitted into four more blocks, and as long as you are giving the refinement levels, the block splitting will occur. And then once you have created your blocks and created the refinement region, then we need to remove the cells from the background mesh so that our STL is visible clearly. So this section will remove the unwanted regions that are present, and this is retained by a specific keyword called location in mesh. And uh, this is very important parameter. I'll display this how this looks, and we can how can we find this. And in this more, the cell volume that is more than 50% are generally retained, rest all are deleted. And we have to specify a point inside our computational domain to get the mesh. And then snap controls, this was occurring in the first section, that was castellation. Now we move to snap controls. In snap controls, we the background mesh and our STL are firmly merged, and this a surface is created using our STL, and we can have a check at the mesh quality parameters, and it generally adjusts its value to get the refined mesh. Okay. And then there is the last part, that is add layers. So this is the final step in the mesh generation. So if you are working in external aerodynamics, so the boundary layer capture, to capture the boundary layer, it is very important. So this is the section that has been provided. So we can specify the number of layers that we are interested in. Here we can see there is only one layer around our airfoil, but you can add gradual layers to your open foam uh, domain of interest. Okay, so yeah, again, we cannot understand without doing anything. So for today's session, I'm taking an external aerodynamic case, and for that, I'm not going to demonstrate how to run the case, but we are just going till the meshing part. So if you can see, I have a diameter, I have a circle, or if we are watching it in 2D, it will look like a circle, but if we watch it in 3D, it will look like a cylinder. So I have my computational domain here, and the uh, diameter of my cylinder is kept as 0.1 meters. Okay. And uh, the distance downstream is 30 times the diameter of my body, and the distance upstream is 10 times the diameter. And likewise it has been split in positive y directions as well, and negative y directions as well. And here we are just naming the inlet patch and outlet patch and the cylinder. Okay. So what we can do is we can do a geometry sketching in any CAD modeling software. So if you see, this is the uh, these are the coordinate axis through which we can see, and we can do it here. Let me go to FreeCAD. I'll open it. Okay, so now FreeCAD has been loaded. Now we are in the FreeCAD environment. You can use any of your CAD modeling software of your interest. I'm more comfortable with FreeCAD, hence I'm using it. So what will I do now is I'll go in the part design, as we are designing the part from scratch, and then we will go in the create body section, and then we'll go in the create sketch section. Now here the xy plane is in the downward section. Either you can click this or you can go from xy plane. So I'm clicking this, and now I am in my xy plane. Now here what will I do is I'll go in the circle section, create circle. I'll use the circle using center and rim points, and here, as I have mentioned, we have to make the geometry at xy plane at 0 comma 0 in any CAD modeling software of your interest. Okay, so now I'll just create this circle, and if you are able to see here, the settings are kept on Blender. If you are used to with any other software, let us say if you are used to with the CAD modeling software or Tinkercad environment, you can keep that. This will be helpful for doing some basic operations like padding and zoom out and zoom in. So I am more comfortable with Blender, so my environment is loaded as Blender. And if you see, the dimensions here are 0.1 mm. The dimensions are in mms. Okay, so now what will I do is I will go in the constraint section, and here I'm constraining my diameter. So if I click my circle, here the diameter is around 89 mm, but for our simulation, all we need is 0.1 mm. So I'll just write 0.1, hit enter. Okay. And now I'll zoom out. So yeah, our circle has been created now. This circle is created at 0 comma 0. Now I will close this. If you are using FreeCAD for the first time, so if the environment is loaded or your STL geometry or your 2D sketch is loaded in a green section, that generally denotes that your geometry is fully constrained and we can move further with any operation. Okay, so now this is our circle. If you are able to see, as it is very small, we have to zoom in a little bit. And now what will I do is I'll do the pad section, and let us say I'm not going to pad this long. I'm just going to pad 1, or let us say point 0.1, point 0.5. It is up to you. Okay, so now yeah, so now here our circle is ready. Now what we can do is we can go in the file section and export this file. Okay, so there is a hotkey. You can just click Ctrl plus E like this. We have to select a circle to choose. Let us name this as first uh, in body. Let us label it as cylinder. So now cylinder has been saved. If we click on cylinder and hit Control E, now it will ask me where I want to save my geometry. Let us save, I'll go here in geometry nozzle, and I will save this as cylinder, and it will be saved as STL mesh. Okay, hit save. Okay, so our file has been saved. We can close the FreeCAD environment. We can discard this, no problem, and we can move further. Now we have to link our geometry. Okay, we are generating a base mesh using block mesh, and we are generating our CAD body using any CAD modeling software. Okay, so if you see the environment, let me load it now. 24. Now I'll write the alias OF9. For today's demonstration session, we are using OpenFOAM 9. And yes, please do not worry about the files. I'm going to send the zip file in the drive folder so that you can access it. So I have created a folder called cylinder. You can name it as per your convenience. To go inside this folder called cylinder, what will I do is I'll write cd, and I'll just write cy and hit tab. So it will on its own understand that what I'm trying to do. I want to go in the folder called cylinder, hit enter, and now again I will list out what is there. Okay, so now there are multiple files. I'm going to give you the cylinder file so that you can also open it and check it on your own. So as we all know, to go in the file manager environment, what we generally do is we type the command called explorer.exe space dot. Okay, so here there are multiple folders. This is the zeroth folder, this is the zero.original folder, this is the constant folder, and this is the system folder. These are the three folders that are very important for your open form simulation. In zeroth folder, we generally store information regarding your boundary condition. In constant, we store our STL file and mesh information along with the fluid properties. And in the system folder, there is information regarding the files that are need to be executed. Okay, so let us go in the constant section. So here there are two folders. I'll delete them first. Okay, so if you load any normal environment of OpenFOAM and go in constant, so if there is no folder called try surface, you can just directly right click here and go in new and make a new folder and name it as try surface. But we are not going to do that as we have already done it here. I'm also deleting the image, and you have to do nothing but save the file in the try surface section of which that you have the file that you have saved here. So let us say uh, let me go in the nozzle. Okay, and here this cylinder file, I have to just copy this file and paste it inside the cylinder folder that I'm interested in. So cylinder is the simulation name. In the cylinder folder, I'll go in the constant folder, and in that constant folder there will be a file called try surface. So I'll paste my STL here. Okay, now I'll refresh it. So now cylinder is here, but as we have already created this file, so we are going to delete it. So our first task is done. We have imported the STL file into the OpenFOAM's try surface folder. Now what we have to do is we have to define OpenFOAM ki what are the edges or what is the feature of this geometry. So for that, what we are going to do is so there are some commands that you have to run to get your things get going. So first we are generating the block mesh, then we are going to write the surface features that are there in your geometry, and then we are going to use SnappyHexMesh utility. So let us go in the environment, and if you are interested, I can show you the block mesh file as well. So here there are multiple files. So out of which today we are going to learn, we have learned about block mesh. Now today we are going to learn about surface features and snappy xmesh tech. Okay. So I'll open VS Code first. You can use any notepad editor. It is just to edit the code. You can use notepad C++, you can use notepad.exe, or you can use VS Code, or you can use gedit, that is of native Ubuntu's environment. You can use nano text editor, or there are multiple text editor that you can use. So now I'll open everything one by one, and I am going to paste it here. So first thing first, this is the block mesh dictionary. As we know, what we have done is we are going to convert with meters, same dimension. We are not scaling anything. And now here we have just defined the points of the rectangle, and the padding is of 0.5. Okay. Then we have defined a one block, and in that block the cells in x-axis are 100, in y-axis are 60, and in z-axis there is 1. So this means ki there will be only one cell in the z-axis, so our simulation will be 2D. And we are not going to make any curve edges, so we are skipping this edges section. And now we come in the boundary. Here we are defining what are the patches here. So inlet, outlet, front patch, back patch, everything has been defined. Okay, now we are going in the surface features extract. Just let me turn it to C++. So first thing first, this is open form version that is being loaded. The format in which we are saving the file is ASCII. What is this? This is a dictionary. And what is the name of this dictionary? It is surface features dict. In OpenFOAM 2412, this dictionary is also known as surface feature extract dict. So please do not get confused. It is just the nomenclature of the files. In OpenFOAM 9, it is surface features dict. and in OpenFOAM 2412 it is surface features extracted. Okay, so this is the basic small file. So here, first thing is the surfaces. Okay, so as we are working with the cylinder only, we are going to write the name. Same name we have to give, the name that we have stored in constant try surface. Okay, so this was the name that I saved my STL using cylinder.stl. So in surfaces section, I'm just specifying the same. Okay, so yeah, now in the surfaces section, I am just going to keep the name of the file that we have defined in the constant try surface section. The name of that file was cyl.stl. We can see here as well. If we go in the constant section and in constant try surface, the name is cyl.stl. Okay, so same name has been allotted here. This include angle, I'll tell more about this in the later section once this session is over. For now, we are keeping this. Just know this as this is an angle that you have to take to understand the geometry properly. In this section, we are just capturing the edges of our geometry. I'll explain this once the session is over, but for now, just hang on and let us keep this angle as 150. And subset features, we are not going to make any changes here. Okay. And once this is done, now we have to execute block mesh. So as we saw the commands, first is block mesh, then is surface features, and then it is snappy. So I'll run block mesh, hit enter. Okay, so it has created the mesh. Uh, there are four patches, and the name of the patches is outlet, fixed walls, front, and back. Okay, so now I want to do surface features. Surface features. If I write surface and I write F and hit tab, it will try to capture what I'm trying to say. Surface features. See, surface features. So now I'll hit enter. Yes. Uh, okay, so it is surface features. I was writing surface features, so it was throwing an error. And now if you see, I'll zoom out a little bit. So what this is doing is, this is reading the directory that we have written, surface feature strict. What is the name of the surface? It is cylinder.stl. In short, we have written cylinder, and it will load the information regarding our geometry, that how many triangles are there, vertices are there, and what is the bounding box of this geometry. And then it is going to reconstruct everything, and these are the information about your geometry. And it is writing extended feature edge mesh. So it is writing a folder called extended feature edge mesh to constant, and extended feature edge mesh as this. And it is also writing the feature edge mesh in the constant try surface cylinder.emesh. Okay, and this is the execution time that it took. It was 0.01 seconds. If we do it again, so the execution time was 0. Okay, so now we have loaded the information regarding the inlet and regarding our STL to OpenFOAM. We have given the information to OpenFOAM, and now we are ready to go into SnappyHexMesh and write it. So this is the SnappyHexMesh utility. We'll go upwards. And again, so yeah, this is OpenFOAM version 9. Format is ASCII. Class is it is a dictionary. And what is the name of dictionary? It is SnappyHexMesh. Please note that there is no difference in the syntax of SnappyHexMesh for OpenFOAM 9 and 2412. You have to execute the same commands. Also, for your better reference, this file is a big, so this is almost around 200 lines of code. Majorly here are comments given, so whenever you are working with it, you can understand everything that is given here. Okay, so I have given the comments here, so if you are specifying anything, you will get to know what we are doing. So let us go one by one. So the first thing is castellated mesh. As we have seen, the workflow of SnappyHexMesh consists of three parameters. First is castellated mesh controls, second is snap controls, and third is add layers. Okay, so these are the three sections. If you we have to as a default we have to set these two versions as true. Add layers, it is up to us. If you want to switch it off, what you can do is you can just comment this out and write false here and give the semicolon, save it. So if you want to set it as true, you can just write true, and if you want to turn it off, you have to write false to switch it off. Okay, so now here what we are doing in the geometry section, we are going to load the information about our geometry. Okay, so as we are only having cylinder here, so it is we are writing as cylinder.stl, the format in which we have exported the stl. So as you can see, it describes all the input geometry that is required by SnappyHexMesh. And cylinder.stl, so this is the name of the geometrical entity that we are working with, and here is the allowed file section, so which files can be loaded here. Okay, so then the type of this file is tri-surface emesh. So if you see, we have written the emesh folder in feature edge mesh, constant tri-surface as cylinder.emesh. Okay, so we have written emesh folder as well, and we are calling it in this geometry part. So this will be tri-surface emesh. And what is the name of the emesh again? You can see here cyl.emesh. So we have just defined it here. This is user specified, you can name it on your own. Refinement box, so let us say if you want to add some refinement near your cylinder. If I go here, so this is your external aerodynamic body inlet. Your upstream velocity is coming from left hand side, and if you want to capture any wakes, if you are doing any transient simulation, or if you are working on any non-dimensional number like Strouhal number, so you have to particularly capture wakes and eddies that is forming past this body. And for that, either you can give a refinement box, or you can give refinement in both positive and positive x-axis and a positive y-axis in upwards and downward section. Or what you can do is you can just create a refinement section box. So we are doing the refinement section box. So here this is refinement section box 1, and this is a searchable box, so that I mean we can give the coordinates here. The coordinates are given as follows, and same we are giving two refinement box to capture the eddy properly. Okay, the coordinates are given again. You can go along it, and it is pretty self-explanatory. Okay, and now we are coming to the first part of SnappyHexMesh. So this was about the geometry information that we are importing, and this part is the first major thing that you are going to deal in SnappyHexMesh. So majorly we keep these values as default. We do not try to make changes here until and unless you know what is occurring. So if you are working in parallel processors, these two commands are important. Let us see them one by one. So this is castellated mesh controls. So first thing is maximum local cell. Local cells will keep the number of cells in your single processors. So this will define how much number of cells are required per processors. And this is the maximum global cells. So in this section, your system will be defined ki how much total cells are required for your simulation. I've given the comments for everything, the maximum number of cells that are allowed per processor. So let us say if you are meshing using two processors and there are 20,000 cells, so one processor will be allotted 10,000 cells, and the another processor will be allotted 10,000 cells. Okay, and the refinement cells, that is if you are, let us say, iterating the refinement, if you are iterating it, so how much number of refinement that is allowed. So let us say if you are refining with level 2, so there should be minimum 10 cells per refinement iteration. Okay, And this load balance is generally associated during refinement, and the cells between levels, so the buffer layers that we want for different refinement levels, is also defined. Generally, if you are a newbie, we generally do not change any settings here. We keep the settings as default and move further. And then in the features section, if we want to intersect our geometry with the background mesh, so we have to define this geometry here. What is the extension of the geometry? It is emesh. And what are the refinement level that we are giving is two levels of refinement. Okay, so this is the feature level refinement. Now we will go to refinement surfaces. Okay, again, this is the single part of your castellated mesh control. uh, where we want our surface refinement, we want our surface refinement on the patch called cylinder, and this is the user specified geometry. And in that, what level of refinement we want, it is five levels of refinement in the x section, and five levels of refinement in the y section. So this defines as the minimum and maximum level of refinements, and it is going to mesh only the surface of your geometry. And if there is any particular patch info for your refinement, it can be given as wall. No other type is allowed. Okay, so this refinement section is done. You can play with these settings once your geometry is created. This resolve angle is used to capture the maximum cell size. I will display this using paraview. So if you want to capture everything with along with the edges, you can keep this angle. Generally it is between 0 to 100. So if you give very high angle here, not uh, not every edge or parameter will be captured. And if you give very low angle, so it will result in capturing everything. So we have to come up with a normal standard value. So here we are giving 5. Okay, and now if we want a region wise refinement, so what we can do is, in the refinement there, we are giving two levels of refinement. First is refinement box 1, and we are giving it inside, and there will be four levels of refinement. And along with refinement level 2, again it is inside, and refinement level of 3. Okay, so once this is done, this is very 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 important section in your snappyx mesh. This will define how your mesh is being created. So what you can do is, you can keep this as a default for now. But if you are doing any high quality message generation, what you have to do is, we have to specify a point in our geometry. Okay, so if I open paraview and load the stl file with the background mesh, let me do it for you. Paraview. So paraview is loading, and I'll open dry surface. I'll open the foam.foam file. So first thing here you should be able to see is that, let us keep it to 2D. Okay, so this is the background mesh that is being generated. Let me pull it back here. Okay, so this will be the background mesh that is going to be created. Let me uh, change the opacity to 0.1. Okay, so this is going to be the geometry. And if I load my stl here, the constant dry surface cylinder.stl, apply. So you can see how is the geometry is going to look like. Our cylinder will be loaded at 0.0.0 in the xyz direction, as we have created it in FreeCAD. You have to just make sure that your points are clear. Okay, so this is the stl and this is the foam file, and we are going to merge it. Okay, and once you do this, you have to go down and turn on the access grids. So if you are working on an external aerodynamic simulation, what you can do is, you can specify a point that is 0 in x, 0 in y, and same for 0 in Z as well. Okay, let me switch it to C. So here, the z-axis is going from 0 to minus 50. Let me zoom it a little bit. So z-axis is going from 0 to 0.5. So this point will work. But if you are working on an internal flow simulation, then what you have to do is you have to specify a point inside this cylinder. Okay. So this point will become near around 17 in positive in x, minus 17 in negative x, uh, minus 2 in negative y, and likewise in negative z, and we have to offset it. So for that, what you can do is you can just give 0.001 in positive x, 0.001 in positive y, 0.001 in x-axis as well, so that what it will do is it is just used as the point to load information about the mesh file in openform. So what you can do is in the filter section you can plot that point as well. So this is a hotkey. So if you press Ctrl plus Shift, this tab will be opened. And now if I load the point source and hit enter, so now I get the axis coordinates as well. I can plot the point here. The point is 0 comma 0 comma 0. I'll hit apply and I'll change the color style of it. So I'm making it as red. So if you see, it is not colliding with any meshes, as I have uh, reduced the opacity as well. It is not coinciding, but if in some case it coincides, so you have to just give it a bit of offset. Let us say 0.0.1, 0.0.1. Okay, and now if I hit apply, the point will get deferred. Okay, so the point has been deferred now, but as it was working at 0 comma 0 comma 0 as well, we are not going to make changes here. Okay, so now moving to the further section of our
Paris,
SnappyHexMesh.
just
So
one thing.
yeah, huh? Hmm?
In ParaView, no, when you load the cylinder, you can show them the information
Hmm?
tab also in case you want to find the coordinate system
Hmm?
of your geometry in space.
Hmm, hmm, hmm.
Yeah.
Okay, so if you uh, if you click your cylinder.stl, you have to just hit data axis grids, and the information regarding your STL will be also loaded, and in the information the total bound box will be also represented, that in x-axis it is going from minus 15 to minus 14.5, and likewise for y and z axis as well. And same for foam.foam, the bounding box that we have defined in block mesh is also represented. So the total number of division in x-axis is 50, in y-axis it is 30, and in z-axis it is 0.5. Okay, so this is done. Now we'll move towards the next section, that is snap controls. We generally do not do anything to this section as of now. Just if we are defining the feature angle explicitly, we hit it as true, and if we are defining the feature angle, if we want open form to capture the feature angle on its own, we keep this as true. But we generally keep this as true and define the features that are given here. Okay, so you can read about this once we are done, and I'll share this file with you as well. And this is the add layers control. So in add layers control, we will get the layers, boundary layers around our geometry. And in this section, the layers section, on which patch we want the layers, so we can do the patch name. We have to do the patch name. So the patch name will be the same that we have defined in our tri-surface constant folder, that is CYL. It is also user defined, and the number of layers that we are interested in. Okay, and once this is done, as we have not kept layers control, we have kept the layers control section off. So this time it will not generate any boundary layer thickness. But if we keep it as true, it will be turned on. So this is the expansion ratio. So how the refinement between two cells should work, so we are giving it as 2, but generally in ANSYS or other softwares you can see the expansion ratio as 1.2 or 1.1. Okay, so you can give your expansion ratio using this. And this is the first layer and final layer thickness. It is up to you that which value that you want to define. If you are defining the final layer thickness, then you don't have to define the first layer thickness. Okay, so you have to define either one of them. And here we have given the final layer thickness, but you can specify the first layer thickness too. There is a basic calculation associated with this. uh, I have given the resources to do that. And the thickness that will be needed for our boundary layer, it is 0.0.1. And this is that if we want to add any layer in consecutive cases, if we can do that. This is the angle that is associated between two files. uh, Everything is given here, you can just check it once. Due to time constraint, I'm skipping it because I have to show some different parameters as well. So now once it is done, what we can do is, just to check that we are in the right directory, what will I do is, I'll now write snappy hex mesh override. If you look carefully, we have just defined castellated mesh and snapping. We have set the layer addition as false. So now the type of mesh that will be created, it will not consist of any boundary layer. Okay, I'll hit enter. Now this refinement has started. In the meantime, I'll just demonstrate, if you want to run your uh, simulation in parallel, how you can do that on Linux. So let let this be done, so we can see that. So this is the command lscpu. In lscpu, there is a basic formula that total number of physical cores, it is number of cores per socket into number of sockets. So this is for my system, so I have total physical cores as 8 cores, and total number of cores on which I can run my simulation is total number of physical cores that we have calculated from this part into number of threads per core. We can see this if I do lscpu and hit enter. So here there will be threads per core, that is 2, and cores per socket, it is 8. So physical cores are 8, and total number of physical cores into threads per core, that is 8 into 2, 16. Okay, so either you can do this, or you can go in your task manager, and here in the performance section you can see total number of cores is 8 and total number of logical processors is 16. So this is generally used for parallel flow simulation, or even for parallel meshing. We generally hit turn this on. Okay, so as we can see, our mesh has been created. So cells per refinement level, in the 0th refinement level there were 5200 cells, and in the 5th refinement there are around 78,200 cells. Okay, this is checking the mesh, how is it, and this will list out all the necessary parameters that are there, and this will display the total number of time in which the mesh has been completed, and it will also show that the meshing is done without any errors. Okay, so to view this mesh, again we have to make a foam file. I have already created a foam file. So what you can do is go here, delete this, open, and before proceeding, I'll just turn back to my normal view so that I can visualize it in a better way. Display, and just keep the changes. Yeah. So I'll go in file. I don't want to load my STL now. I want to load the foam file and hit apply. So it will take a bit time. But now, as we previously saw, there was a background mesh, and we have created a STL file, and now it has been perfectly merged with the body. Just keep in mind the thickness of the STL and the thickness of this background mesh that we define in block mesh must be the same. So here the thickness of the cylinder was zero point 0.5, and the thickness of the block mesh was also zero point 0.5. Okay, so let me go to surface with edges. So see, here are two refinement box that are occurred. And if I try to zoom in a little bit, let me switch it to 2D view. So if we zoom in a little bit, so here you can see there is no boundary layer. Okay, there is no boundary layer. So to generate the boundary layer, we have to switch this, we have to turn the setting as on and go directly downwards and specify the number of layers that we are interested in. So here we have given the number of, let us say 5. Just save the file, go backwards, run block mesh again, block mesh, and run snappy. Is anyone
But
speaking?
yeah, but is instead of
Huh?
on top, you'll have to put true. In the snappy hex dict,
Yeah, okay.
you've written it as
Okay,
on.
okay, okay. Huh, true. Okay. Huh. So we have to just hit it as true. Okay, save this file. We have defined the number of layers as 5 now here, and run block mesh and snappy hex mesh override. So what this override command does is it deletes the previous mesh and it will regenerate your mesh again. Okay, so as this is going on, uh, so yes, I have defined what is SnappyHexMesh in the directory, and now we are going to get a brief idea of what is Y plus. Someone's mic is on. Uh, Professor Bipin, are
Right.
you having any doubts? Okay, okay, thank you, sir. Thank you. So why is Y plus important? So this is the air file. This is the when we are doing an experiment on this, and we are trying to capture the boundary layer here. So Y plus is a non-dimensional wall distance that is used to evaluate the mesh in turbulent flows. So in our day-to-day cases, there will not be a case which will have a steady state simulation. Majority of the cases are done as turbulent and treated as transient. So to resolve this and capture the boundary layer accurately, we use Y plus. Okay, what are the important features of Y plus? That it ensures the correct boundary layer resolution. Y plus also helps us to capture the turbulence properly, and it helps us to choose the wall treatment. uh, so keeping the Y plus value is up to us. So if we are running a large eddy simulation, we generally keep the Y plus value as 1. When we keep the Y plus value as 1, uh, let us say this is your wall and this is your free stream velocity. So in the boundary layer there are some sections, that is sub layer or buffer layer, that is we say, and the fully turbulent region or log flow region where the eddies are being formed. So this is the second layer, and this is the outer layer. Okay, so it is up to us that if we keep the Y plus equal to 1, then we are capturing the viscous sublayer as well. So we are refining it at a very fine level, and we are capturing the buffer layer as well. If we keep the Y plus value to 30 to 300, so we have to use a turbulent model called K omega or K omega SST. You might have heard about it in ANSYS Fluent. So if we are working on low Reynolds number, we generally resolve the viscous sublayer. But if we are working in turbulent flow or turbulent region, then we keep this as K omega or K epsilon with some wall functions, and we can define the Y plus value. And to calculate y plus, so there are multiple y plus calculator online available, but I personally prefer calculating my y plus value using some analytical methods. So it is very simple. uh, there are some assumptions that we are doing, that the working fluid that we have taken is air at 15 degrees Celsius. The density of air is 1.225 kg per meter cube. The dynamic viscosity of the particular fluid is 1.8 into 10 to the power 5 kgs per meter second, and the free stream velocity or the inlet velocity is 5 meter per second. Okay, so first thing first, we are just going to calculate the Reynolds number. It is pretty forward. The Reynolds number's formula: density into free stream velocity into characteristic length, divided by the dynamic viscosity. So we have just given the values here, and we have got a Reynolds number value of 34,000. That that comes under laminar region for external aerodynamics. If you are doing an internal aerodynamics, internal flow simulation, then this is turbulent region. Okay, then we are going to calculate coefficient of friction. So cf value is defined for internal aerodynamic internal flow differently, and for external flows it is differently. So for external flows, the cf value is 0.0058 into Reynolds number to the power minus zero point 0.2. So I have just put at my Reynolds number here, and I have got my cf value. Okay, so we have done two steps, and now we have to calculate the shear stress. It is denoted as tau w. So formula of shear stress is 1 by 2 into cf into density into free stream velocity. Okay, so 1 by 2 is denoted as 0.5. Cf value that we have generated from equation 2, see cf value from equation 2, this is the density, and this is the free stream velocities square. So I'm having these values, and now I got my shear stress values as 0.0110100. Okay, once the shear stress is calculated, then we will move further to calculating the velocity shear. Velocity shear is nothing but your shear stress divided by the density under root of under root. So the tau w value is from the equation number 3. We are denoting it as equation number 3, and we are inputting the density value. So we get velocity shear as 0.0947 meter per second. Okay, so this will we will write it as equation number 4. And now we are going to calculate the first cell thickness, that is y. So y plus, that is the targeted y plus that we are aiming for. As I said, we can keep the y plus value as 1 if we are resolving the viscous sublayer, and we can keep the y plus value in between 30 to 300 if we are using any particular turbulence model. So it is up to 1. In this case, we are resolving the viscous sublayer, hence I have kept the y plus value as 1, and this is the dynamic viscosity divided by u tau, that is the velocity shear, into density. Okay, this will give you a value in meters. We have to, either we can give this value in meters, or we can convert this to as well. And if you see SnappyHexMesh file, so there is a file called first layer thickness. So you can specify it here, and you can comment it out the final layer thickness. Okay, so if you don't know about how is your boundary layer is transitioning, so you generally keep the final layer thickness on. But if you know how you can calculate the y plus value, so you comment this out and give the final layer thickness with an expansion ratio of 1.2 to 1.1. Okay, once this is done, so now these are the commands that we are writing. But let us say the body domain is pretty big, then we have to decompose the domain into some sections. And again, we are running the block mesh, then we are running the surface features, and then we are running decompose par. So decompose par, if I go in this file and open this, decompose par is also one of the files that is located in the system folder, same as where surface features, SnappyHexMesh, and block mesh are located. I'll just open this. So this is the number of domains that you want to divide your geometry in. So for now, I'm going to use, let us say I'm going to use 8 four processors. So for that, I will define the number of processors that I'm using. How to find out the processor? As I told, you have to just do lscpu. So this will point out everything that is there. Or what you can do is you can write a command called nproc. So it is the same for calculation. If you want to just skip your calculation, you can directly write nproc. Or if you want to identify key what is information about your system, you can do lscpu. And with the analytical manner, you can calculate the number of processors that are available for your simulation. Okay. So this is a method. There is a method called scotch, in which we are going to decompose. In scotch method, what generally happens is the interpolation between the four processors is very smooth. So in industries as well, we generally use scotch. But there are again various methods called hierarchical or um other methods as well. So you can find out about that more, or I can give you a detailed explanation in a document for this. Okay. We execute decompose par. Let us do that. Decompose par. So now, as we have kept our files as four, the terminal has given me an output that it has transferred, or it has separatized my domain into four processors: processor 0, processor 1, processor 2, processor 3. The uh, the sharing is done. Time that it took was 0. Processor 1 field transfer is successful. Processor 0, processor 1, processor 2, and processor 3. So in all four processor, the field transfer is done successfully. And now what we can do is we can use this command mpi. Mpi is used for your parallel simulation. Mpi run -np. Np is number of processors. Here we have 4. There was the command was for the, 10 processors. Then the utility. Okay, snappy hex mesh. And then where we want in parallel, so we will write hyphen parallel override. And then your parallel decomposition meshing will also start. Okay, see, once this is done, I can show this using a post processing tool. In the meantime, what we can do is I'll just transfer my foam file into every processor. So this file will go to this. Okay, control c, control v, control v. So what am I doing is I am transferring the foam file to every processor so that we can visualize our files decomposed domain easily. Let us see. It is taking a bit of time. Okay, so finalizing parallel run, it is successful. Now I'll just delete this. I'll open files and same location, processor 0. And in processor 0, I'll open the foam file. Mark it with surface with edges, and I'll change the color to gray. Okay. Likewise, I'll do for every other processor. Processor 1, apply. Now see, the lower section has been generated. Again, let us say we can mark it as blue and switch it to surface with edges. Open processor number 3, foam.foam, apply. Again, another section has been loaded. Let us skip right here. Hit surface with edges. It is done. And now what we will do is open our final processor, foam.foam file, hit apply. It will take some time, and now it has loaded the other last domain as well. To color it, maybe we can give it as yellow and change it to surface with edges. So here you can see our domain was changed into four, was decomposed into four folders, four processors, and we have colored them differently. So processor 1 is handling by green, colored by green. Processor 2 is colored by blue. Processor 3 is colored by red, and the rest everything has been dumped in processor 4, and it is colored by or marked by yellow color. Okay, and if you zoom in a little bit, so here we can see the boundary layer thickness as well. Okay, if you zoom in too long, and if you have a low RAM, you might not be able to do that, but you have to zoom in a little bit to see the proper development of the boundary layer as well. Okay, so yeah, this is done in decomposition, and this is fluent to foam utility. We are not going to learn about this. And what is next for you guys is key. Now we have generated a circular cylinder. What you can try do is key, you can generate a semicircle, pad it, and export it to SnappyHexMesh. Just repeat all the steps that I have given in the file, and just change your name to cylinder to any name. Let us say cylinder. So it will be denoted as semi-cylinder. You have to change the names, execute the commands that I have taught, and you should be able to execute or able to see this mesh here. And likewise, for some, if you want to do any square or rectangular block, you can do that as well. And also I have an airfoil geometry as well with me, that has been run on OpenFOAM 9. So if you can see, this is an S1223 airfoil, and here I got some triangulation errors while importing to OpenFOAM, but that I have resolved using OpenFOAM, but Fluent Meshing was not able to do that. So I'll be sharing that file as well. So if you are interested to mesh the airfoil, you can do that as well, and you can take up this as an assignment. Okay, so thank you for your time and patience. I know SnappyHexMesh is a bit complex utility, but with some persistent time and effort, I'm pretty sure you should be able to generate the high quality meshes. If you have any doubts, you can write us to the contact FOSSEE CFD. The same email has been shared with Professor Bipin and Professor Ashish. And yeah, that's all from my end. Thank you for your time.